Welcome to this problem walkthrough. In today's session, we'll explore problem number 1623, count ways to make array with product. We'll break down the problem, analyze different approaches, and understand the trade-offs in complexity. Let's dive in. This problem is about counting the number of ways to construct an array of size n such that the product of all its elements is exactly equal to a given number k. Each element in the array must be a positive integer, and since the number of possible combinations can become very large, the result must be returned modulo 10 to the power of 9 plus 7. The input consists of two integers, n, which represents the size of the array, and k, which is the target product. The output is a single integer representing the number of valid arrays that satisfy the given conditions. This problem challenges us to consider how to compute these combinations efficiently while adhering to the constraints. Let's explore an example to better understand the problem. If n is 2 and k is 6, we need to find all arrays of size 2 where the product of the elements equals 6. There are exactly 4 valid arrays, 1, 6, 6, 1, 2, 3, and 3, 2. Each of these arrays satisfies the condition that the product of the elements equals k. This highlights that we're not just concerned with the values themselves but also their arrangement within the array, as different permutations count as distinct solutions. Now consider an example where n is 3 and k is 12. In this case, we need arrays of size 3 where the product of the elements equals 12. There are 10 valid arrays, including combinations like 1, 1, 12, 1, 12, 1, 12, 1, 1, 2, 2, 3, and so on. Each of these arrays satisfies the product condition, and the permutations of the same numbers in different positions are treated as unique arrays. This illustrates how the number of valid arrays can grow quickly as n increases and how important it is to consider all possible factorizations and their arrangements. Finally, let's look at a simpler example where n is 1 and k is 1. Here, the only valid array is 1, since the product of its single element equals k. This brings us to the constraints for the problem. The size of the array, n, can range from 1 to 100, while the target product, k, can go up to 10 to the power of 4. The result must be returned modulo 10 to the power of 9 plus 7 to handle the potentially large number of combinations. Some edge cases to consider include arrays with a single element, scenarios where k is a prime number, and cases where the target product is unreachable due to the constraints on n and k. Efficient computation is key to solving this problem within the given limits. To solve this problem, we first considered the brute force approach. The intuition here is simple. We iterate through all possible arrays of size n and check if the product of the elements equals k. For each array that satisfies this condition, we increment a counter. However, this approach quickly becomes impractical for larger inputs because the number of potential arrays grows exponentially with n. This results in a time complexity of O, k to the power of n, where k is the upper bound of the array elements. This exponential growth makes the brute force method computationally prohibitive. To address this, we turn to an optimized approach that uses prime factorization and dynamic programming. The key observation here is that the product k can be broken down into its prime factors raised to certain powers. For instance, if k equals 12, its prime factorization is 2^2 asterisk 3^1. By focusing on these prime factors, we can transform the problem into distributing the powers of those primes across the n elements of the array. To achieve this, we define a dynamic programming state where dp, I, j, represents the number of ways to distribute the first I primes across j array elements. Using combinatorics, specifically binomial coefficients, we calculate how the powers of each prime can be distributed among the n elements. This allows us to efficiently break the problem into smaller, manageable subproblems. This optimized approach significantly reduces the search space by focusing on the prime factors of k rather than all possible arrays. By doing so, the time complexity is reduced to O, n asterisk m, where m represents the number of distinct prime factors of k. This makes the approach much more scalable for larger inputs. Now, why choose prime factorization in dynamic programming? First, it leverages the inherent mathematical structure of the problem, allowing us to work with a reduced state space. Second, it avoids the redundant computations that are unavoidable in brute force methods, making it far more efficient. Finally, it is well suited for handling larger constraints, as the computation scales proportionally with the number of prime factors instead of the exponential growth seen in brute force. Of course, there are trade-offs to consider. While the brute force approach is easy to implement, it is far too inefficient for large inputs. On the other hand, the prime factorization and dynamic programming method is more complex to implement, but it offers significant performance benefits. Alternative combinatorial methods could also be explored, but they would likely involve similar or even higher complexity compared to this DP approach. The key breakthrough in solving this problem lies in the realization that we can focus on distributing the powers of the prime factors of k across the elements of the array. This insight dramatically simplifies the problem by reducing the state space from all possible arrays to just the prime factor distribution. Instead of dealing with the combinatorial explosion of trying every possible array, we concentrate only on the mathematical structure of the prime factorization. This shift in perspective is what makes the approach not only feasible but also efficient, even for larger inputs. By leveraging this observation, we avoid unnecessary computations and focus our efforts where they matter most, leading to a much more elegant and scalable solution. To solve this problem, the first step is to clearly understand the input and the task. We are given two inputs, n, which is the size of the array, and k, the product that all elements of the array must multiply to. The goal is to determine the number of such arrays that can be formed. At first glance, this problem inherently involves factorization, since each element in the array must be a factor of k. Now, one way to approach this is through brute force, generating all possible arrays of size n and checking if their product equals k. However, this approach becomes computationally infeasible as n or k grow larger, because the number of arrays to evaluate grows exponentially, at a rate of k(n). To overcome this, we need a more optimized strategy that focuses on the factors of k and leverages backtracking to efficiently explore valid combinations. The key idea in the optimized approach is to narrow down our search space by focusing on the factors of k. If x is a factor of k, then k/x is also a factor, which allows us to construct valid combinations more efficiently. The first step is to generate a list of all factors of k. This will serve as the pool of candidate elements that can appear in the array. Next, we use a backtracking function to recursively build arrays of size n. At each step, we append a factor to the current array and adjust the remaining product accordingly. The function has a clear base case: if the array reaches size n and the product of its elements equals k, we increment a counter. To improve efficiency, we include pruning conditions so that we stop exploring paths that are guaranteed to fail. For example, if the current product exceeds k, there's no point in continuing further down that path. Similarly, if the array grows beyond size n, we terminate that branch. This combination of factorization and backtracking drastically reduces the computational complexity compared to the brute force method. Using the backtracking approach, we start by calling the recursive function with an empty array and the original product k. The goal is to incrementally build valid arrays while keeping track of the total count. Once the backtracking process completes, we simply return the counter value, which represents the total number of valid arrays. It's also important to consider edge cases to ensure the algorithm is robust. For example, if n is 0, it's impossible to form any arrays, so we should return 0 immediately. Similarly, if k is 0, we need to handle this separately because 0 cannot be divided by other numbers. Another edge case arises when k is a prime number. In such scenarios, the factors of k are limited to 1 and k itself, and the solution depends on the value of n. For instance, if n is greater than 1, the only valid array might consist of k followed by 1s. By addressing these cases explicitly, we ensure the algorithm handles all possible inputs correctly. The implementation of the optimized approach involves three main steps. First, we factorize k by iterating from 1 to the square root of k. For each potential factor, we check if it divides k without a remainder. If it does, we add both the factor and its complement to a list, ensuring we capture all divisors of k. Next, we define the backtracking function. This function takes the current array and its product as arguments and explores all possible ways to build valid arrays. If the array reaches size n and the product equals k, we increment the count. Otherwise, for each factor, we recursively extend the array, provided the resulting product does not exceed k. Finally, we initialize the count to 0, call the backtracking function with an empty array and a product of 1, and return the count. This implementation efficiently combines factorization and recursive exploration to solve the problem. To further optimize and understand the algorithm, let's break down the key data structures and their roles. First, we use a list to store the factors of k. This allows us to quickly access these factors during the backtracking process. Second, we use a counter variable to track the number of valid arrays found. This can be implemented as a simple integer or, in some cases, a mutable structure like a one-element list to work within a recursive context. The recursive stack is another critical component, as it stores intermediate states during the backtracking process. The depth of this stack is bounded by n, making it efficient for moderate input sizes. Finally, the algorithm is robust because it explicitly handles edge cases such as n being 0, k being 0, or k being a prime number. By ensuring the algorithm accounts for these scenarios, we can confidently apply it to a wide range of inputs. Analyzing the complexity of the algorithm provides further insight into its efficiency. The factorization step, which involves finding all divisors of k, takes k time. This is because we only need to check divisors up to the square root of k. The backtracking step depends on the number of factors and the size of n. In the worst case, the number of recursive calls is proportional to f to the power of n, where f is the number of factors of k. Combining these, the overall complexity is k plus f to the power of n. While this is still exponential in n, it is significantly more efficient than the brute force approach, which has a complexity of k to the power of n. By leveraging the reduced search space from factorization and the efficiency of backtracking, this algorithm provides a practical solution for a challenging problem. Here, we start by importing the comb function from the math module, which will help us calculate combinations efficiently. Next, we define a class called solution and create a method named ways-to-fill-array that takes a list of queries as input. Inside this method, we define a constant mod with a value of 10 to the power of 9 plus 7 to ensure that all calculations are performed modulo this number, preventing overflow and maintaining efficiency. To handle the prime factorization of a number, we define a helper function called prime_factorization. It takes an integer number and returns a dictionary where the keys are the prime factors and the values are their respective exponents. The function uses a while loop to iteratively divide number by potential divisors, starting from 2, while checking if the divisor squared is less than or equal to number. If a divisor is found, we increment its count in the dictionary and reduce number accordingly. Finally, if number is greater than 1 after the loop, it is added as a prime factor with an exponent of 1. Another helper function, count_ways, is defined to compute the number of ways to fill the array. It takes two arguments, n, the length of the array, and k, the target product. First, it calculates the prime factorization of k using the earlier function. Then, it initializes a variable ways to 1 and iterates over each prime factor and its exponent. Using the combination formula, it calculates the number of ways to distribute the factors among the n elements of the array and updates ways accordingly, applying the modulo operation to keep the result manageable. Now, we complete the ways-to-fill-array method by defining an empty list called result, which will store the output for each query. We iterate over the given queries, where each query provides values for n and k. For every query, we calculate the number of ways using the count_ways function and append the result to the result list. Finally, we return the result list, which contains the answers for all the input queries. This approach leverages modular arithmetic, prime factorization, and combinatorics to efficiently compute the required values, even for large inputs. Here, we start with the Java implementation of the solution. First, we define a constant mod to handle large numbers and prevent overflow during calculations. The ways-to-fill-array method takes a 2D array of queries, where each query consists of two values, n, the size of the array, and k, the target product. For each query, we extract n and k, and call the helper method countWays to calculate the number of ways to fill the array. The results are stored in an array, which is returned at the end. The countWays method is where the main logic resides. It starts by performing a prime factorization of k using another helper function. Then, it iterates through the exponents of the prime factors. For each exponent, we calculate the number of ways to distribute the factors across the n elements using the combination formula. This value is multiplied into a running product, ensuring that the result remains within the modulo constraints. The prime factorization logic is implemented in the prime factorization method. Here, we use a map to store the prime factors of a number along with their exponents. We start dividing the input number by the smallest divisor, 2, and incrementally move to higher divisors. Each time we find a factor, we update its count in the map and reduce the number by dividing it. Once the divisor squared exceeds the remaining number, we check if the number is greater than 1, and if so, we add it as a prime factor with an exponent of 1. The second utility function on this slide, com, calculates combinations using modular arithmetic. It computes the result iteratively to handle large numbers efficiently. For each step, we multiply the numerator by the current term and divide by the corresponding denominator, applying modular inverses to avoid direct division. This ensures that the calculation remains accurate and avoids overflow. To support the combination calculations, we use two additional helper methods, mod inverse and modpal. The mod inverse method computes the modular inverse of a number using Fermat's little theorem, which states that a mod 2% mod is the modular inverse of a, given that mod is a prime number. This calculation is delegated to the modpal method, which performs modular exponentiation. In modpal, we use an iterative approach to raise a base to a power under modulo constraints. By repeatedly squaring the base and reducing the exponent by half, we achieve an efficient computation. If the exponent is odd during any step, we multiply the result by the current base. The combination of these methods ensures that our solution handles large numbers efficiently while adhering to the modulo constraints. To solve this problem, we start with the first query, where the array size is n equals 2 and the product k equals 6. The task is to determine how many ways we can populate an array of size 2 such that the product of its elements equals 6. The first step involves prime factorization of k. Using the prime underscore factorization function, we initialize an empty dictionary factors and begin dividing k by successive integers starting from 2. Dividing 6 by 2 gives 3, so we record the factor 2 with an exponent of 1. Next, dividing 3 by itself results in 1, so we add 3 with an exponent of 1. This gives us the prime factorization, 2, 1, 3, 1. Once we have the prime factors, we calculate how many ways we can distribute the exponents of these factors across the n elements of the array. For each prime factor, we use the formula com, exp plus n1, n1. For the factor 2 with an exponent of 1, the calculation is com, 1 plus 2 to 1, 2 to 1, equals com, 2, 1, equals 2. Similarly, for the factor 3 with an exponent of 1, the result is also com, 2, 1, equals 2. Multiplying these results gives the total number of ways as 2 asterisk 2 equals 4. We then store this result, appending 4 to the output array. Thus, the final output for this query is 4. Now, we move to the second query, where n equals 3 and k equals 12. Again, we aim to find the number of ways to fill an array of size 3 such that the product of its elements equals 12. Starting with the prime factorization of k, we repeatedly divide 12 by 2, which gives 6 and then 3, adding the factor 2 with an exponent of 2 to the factors dictionary. Dividing the remaining 3 by itself results in 1, so we add 3 with an exponent of 1. This gives the prime factorization, 2, 2, 3, 1. Next, we calculate the combinations for each prime factor. For the factor 2 with an exponent of 2, the formula com, exp plus n1, n1, yields com, 2 plus 3 to 1, 3 to 1, equals com, 4, 2, equals 6. For the factor 3 with an exponent of 1, the calculation is com, 1 plus 3 to 1, 3 to 1, equals com, 3, 2, equals 3. Multiplying these results gives the total number of ways as 6 asterisk 3 equals 18. We then append 18 to the result array, making the output, 18, for this query. Finally, we consider the third query, where n equals 1 and k equals 7. Here, we need to determine how many ways we can fill an array of size 1 such that the product of its elements equals 7. Starting with the prime factorization of k, we check divisors up to the square root of 7. Since 7 is a prime number, we directly add it to the factors dictionary with an exponent of 1, resulting in 7, 1. For the single prime factor 7 with an exponent of 1, we calculate the combinations using the formula com, exp plus n1 n1, which simplifies to com, 1 plus 1 to 1, 1 to 1 equals com, 1, 0 equals 1. Since there is only one prime factor, the total number of ways is simply 1. We append this to the result array, yielding a final output of 1 for this query. In summary, the method works by breaking down k into its prime factors and using combinations to distribute the exponents across the array size n. By multiplying the results for each prime factor, we get the total number of ways for any query. The use of modular arithmetic ensures that the outputs remain within the required range. In this problem, the time complexity of our solution is influenced primarily by two operations, prime factorization and the calculation of combinations. First, during the prime factorization step, we compute the prime factors of the given k for each query. This step relies on trial division, which examines potential divisors up to the square root of k. As a result, the time complexity for this operation is approximately O, sqrt, k. Next, we handle the combination calculations. For each prime factor p with an exponent exp, the formula com, exp plus n1, n1, is used. Python's math.com function allows us to compute combinations efficiently with a complexity of O, min, exp, n, which stems from the factorial operations involved. Since there can be up to O, log, k, distinct prime factors for k, the total cost of combination calculations per query becomes O, log, k, asterisk min, exp, n. These two operations together lay the foundation for analyzing the time complexity of the solution. Building on the earlier steps, we now consider the total time complexity of processing all queries. If there are q queries, each requiring prime factorization and combination calculations, the overall time complexity across all queries can be expressed as O, q asterisk, sqrt, k, plus log, k, asterisk min, exp, n. Shifting focus to space complexity, we start with auxiliary space. The prime underscore factorization function uses a dictionary to store the prime factors of k. Since the number of distinct prime factors is proportional to O, log, k, the space required for this dictionary is also O, log, k. Additionally, combination calculations use only constant space to manage intermediate results. The result array, used to store the outputs for all q queries, requires O, q, space. Combining these factors, the overall space complexity of our approach is O, q plus log, k, where the result storage and the prime factor dictionary are the dominant contributors. When comparing this optimized approach to a brute force solution, the efficiency gains become clear. A naive brute force method would involve generating all possible arrays of length n whose elements multiply to k. This would require iterating through every combination of n numbers that could form the product k, resulting in an exponential time complexity with respect to n and k. Such an approach is computationally infeasible for larger inputs. In contrast, our optimized solution leverages the mathematical properties of prime factorization and combinations. By breaking down the problem into prime factors and calculating combinations directly, we avoid the need to explicitly generate arrays. This mathematical reduction significantly reduces the computational overhead, making the solution far more efficient and scalable to larger input sizes. Finally, let's analyze the best, average, and worst cases for this solution. In the best-case scenario, when k is small, the operations for prime factorization and combination calculations are minimal. Here, both sqrt, k, and log, k, are small values, leading to a lower computational cost. On the other hand, the worst-case scenario occurs when k is large, particularly if it has many distinct prime factors, and n is also large. Under these conditions, the combination calculations, such as com, exp plus n1, n1, may dominate the runtime. For the average case, the cost depends on the distribution of k and n across the queries. Typically, it involves a mix of these operations. Summarizing in big O notation, the prime factorization step takes O, sqrt, k, the combination calculations require O, log, k, asterisk min, exp, n, and processing all queries results in O, q asterisk, sqrt, k, plus log, k, asterisk min, exp, n. The space complexity remains O, Q plus log, K, driven by the storage requirements for the results and prime factors. When solving this problem, there are a few common mistakes to watch out for. First, many candidates overlook edge cases, like handling an empty array or when the target product K is 0. Remember that multiplying by 0 always results in 0, so failing to address this could lead to incorrect outputs. Next, negative numbers can introduce unexpected behavior. For example, multiplying two negative numbers results in a positive product, so if K is positive, you might miss valid combinations if you don't account for this. Another pitfall is using a brute force approach that repeatedly recalculates products for overlapping subarrays. This is highly inefficient and can be avoided by leveraging techniques like prefix products. Finally, you need to be cautious about overflow errors, especially in languages like C++ or Java, where exceeding the data types limit can lead to incorrect or undefined behavior when working with large arrays or large values of K. Another frequent mistake is forgetting to define a correct base case in recursive solutions. Without a proper stopping condition, the recursion might continue indefinitely or produce incorrect results. For instance, if you don't terminate the recursion when K becomes 0 or when all elements have been processed, your solution could fail. Now, from an interview perspective, this problem often tests your ability to recognize optimization patterns, such as the sliding window or two-pointer technique, which are far more efficient than brute force. Interviewers also value candidates who can identify pre-processing techniques, like using prefix products or hash maps, to optimize the solution iteratively. It's crucial to articulate the trade-offs between different approaches, such as comparing brute force with sliding window in terms of time and space complexity. Lastly, be ready to handle edge cases explicitly, such as arrays of size 1 or scenarios where K is negative, as these are common tests in interviews. This problem shares similarities with several other LeetCode challenges, which can help you build a stronger understanding of the underlying patterns. For example, LeetCode 560, subarray sum equals K, involves optimizing for sums rather than products and uses hash map-based techniques extensively. Another closely related problem is LeetCode 713, subarray product less than K, which specifically focuses on counting subarrays where the product is less than a given value. Sliding window techniques play a critical role here. Similarly, LeetCode 1248, count number of nice subarrays, applies sliding window methods but targets subarrays meeting specific conditions. Lastly, LeetCode 325, maximum size subarray sum equals K, explores subarray sums but shifts the focus to finding the maximum length subarray. By studying these related problems, you can deepen your understanding of optimization techniques like sliding windows and hash maps, which are highly transferable across these challenges. There are several approaches to solving this problem, each with its own trade-offs. The brute force approach, for instance, involves checking all possible subarrays. While it has a time complexity of O, n squared, or even O, n cubed, depending on implementation, it's simple to write and requires minimal space. However, it becomes impractical for larger arrays due to inefficiency. A more optimized method is the sliding window approach, which reduces the time complexity to O, n, in most cases and uses constant space. It's especially effective when dealing with constraints like product K, but it may not work as well for cases requiring product equals K. Another powerful method is using a hash map with prefix products, which achieves O, n, time complexity by speeding up lookups. The trade-off here is the additional memory required to store prefix products, making it more memory-intensive. Finally, recursive backtracking can be used to explore all possible combinations, but its exponential time complexity makes it suitable only for small input sizes. Understanding these approaches and their trade-offs is key to choosing the best solution for a given problem scenario. Great work! In this session, we covered the key concepts and strategies to solve count ways to make array with product. Keep practicing and applying these techniques to enhance your coding expertise. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!